In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about fusion of life nuclei in a multi-cluster realization of the three-body problem. It was written by Egorov Mikhail Viktorovich from the physics faculty, Tomsk State University. This work describes a few body dynamics method based on the Faddeev integral equations in momentum space for determining the total cross sections of fusion and breakup reactions with two and three body final channels in the continuum employing a cluster representation of the colliding nuclei. Total cross sections were obtained for the reactions, for example, helium TD and helium TNP, and also so on, in which both the projectile and the target nuclei were treated in a cluster representation. The work also implements a two potential method to determine the Colombo T matrix and to account for Colombo effects in short range dynamics in momentum space. Calculations of the initial state Colombo interface and interaction were performed. Furthermore, an estimate was obtained for the magnitude of the off-shell effect of the Colombo T matrix as well as the magnitude of the atomic electron anti-screening effect on the Colombo interaction of the colliding nuclei. The calculated contribution of the cluster mechanism to the total cross-section of the considered fusion reactions in the kinetic energy range, where T is belongs to 1 kilo electron volt up to 20 mega electron volt, is in good agreement with known experimental data. Introduction section. Nuclear fusion remains a subject of enduring interest for prospective energy applications. For the investigation of nuclei at a neutron drip line and for the validation of microscopic reaction models, see Review 3 and 4 and references therein. For nuclear reactions involving a light nuclei at low energies, when E is less or equal to 1 megaelectron volt, the role of the long-range part of the Colombo react interaction remains a fundamental issue. This includes the effect of the atomic electron screening, for instance, in D3 helium fusion, and the implementation of few body dynamics itself, which necessitates the use of rigorous methods from the quantum theory of a few body systems in the energy quantum. Without delving into details of the various approaches to describing nuclear reactions with explicit consideration of the few body aspect, it should be noted that the few body scattering problem was solved most consistently using the Faddeev equations. These were subsequently generalized to an arbitrary number of bodies and to long-range Colombo potentials in the three-body configuration space. The merging of cluster models of nuclei. See an insightful review on the development of the cluster models with a rigorous treatment of the dynamics of systems containing more than two clusters allows the application of few body dynamics methods not only to nuclei and nucleon neutron scattering, but also to more complex nuclei that admit a cluster representation in their ground state. The use of microscopic cluster approach is primarily presented in the context of studying an internal structure of light and medium nuclei regarding alpha clustering. The probability of target nucleus breaks up into its constituent clusters is evaluated less frequently, and calculations of fusion and rearrangement cross sections in the energy regions when E is less than 20 till 30 mega electron volt and virtually absent Optical models with cluster decomposition for both the target nucleus and the projectile, based on a systematic analysis of experimental data, highlights the regions where the distorted wave-borne approximation fails to adequately capture the specific features of reaction dynamics. The descriptions of complex nuclear interactions through the interactions of their individual configurations starting from single nucleon ones has been established since the emergence of the resonating group method or RGM, which is related to reference 18 and 19. This method initiated the development of microscopic alpha cluster models of nuclear reactions, including these accounting for Pauli blocking and employing generator coordinates. Within the RGM or resonating group method framework, the expansion of the complex nuclear wave function into cluster subgroup enables the description of rearrangement reactions for nuclei with a mass number up to the 10 involving multiple available two-body channels. The description of multi-channel reactions, such as those occurring in D plus 7 lithium and D plus 7 beryllium collisions using the RGM or resonating group method with a cluster representation of the target nucleus, allows by reducing the problem to an effective two-body one to adequately reproduce not only the spectra of the target nuclei but also the astrophysical factor of the reactions under consideration. The integration of the RGM with microscopic nuclear models based on NN potential, including effective field theory, as well as the no core shell models or NCM, enables the elevation of cluster-based reaction treatment to a microscopic level. One can also note that the successful combination of the FADF integral coefficients used to determine the cluster wave functions of the lithium-11 halo nucleus with a Glauber scattering model at 60 megaelectron-volt nucleon, which accurately captures the differential quasi-elastic scattering of lithium-11 by carbon-12 nuclei. For the study of reactions between light nuclei, the continuum discretized coupled channels or CDCC method should be highlighted as it has proven effective in describing cross sections for elastic scattering, breakup, and fusion of weakly bound light nuclei while accounting for Colombo effects. This approach utilizes cluster partitioning for the target and for projectile, subsequently reducing the problem to an effective two-body one. For light nuclei, this approach has been successfully applied to neutron and proton-induced breakups reactions of lithium-7 and lithium-6 isotropy into alpha minus T and alpha minus D cluster configurations, which describes the ground states of these nuclei respectively. The complexity in describing fusion and rearrangement reactions is dictated by the selection of appropriate boundary conditions in configuration space for the eigenfunctions of the channel Hamiltonians. The problem of choosing boundary conditions in CDCC method can be somewhat compensated by introducing an imaginary part into the potentials. However, the applicability of DC CDCC method for a unified description of rearrangement and breakup of reactions into three or more fragments remains an open question. The technique of expanding the multi-component wave function or a complete set of the Gaussian functions, which are eigenfunctions of all channel Hamiltonians of the interacting nuclei, allows for minimizing the issue of matching asymptotic conditions for various reaction channels by increasing the number of coupled channels and explicitly utilizing all equivalent sets of Jacobi variables. This enables the treatment of two-body and many-body channels in a unified manner. These procedures for determining the matrix elements of the transition operator is analogous to solving an eigenvalue problem with the variation of unknown complex constants. making this Gaussian basis expansion method unified and applicable to various problems, yet highly sensitive to the basis size. This approach has been extensively developed by describing the properties of large nuclei, including neutron-rich nuclei, and for determining the binding energy of the hypernuclei using the cluster representation. In the momentum space, the Faddeev integral equations for the three-body scattering matrix don't explicitly depend on the boundary conditions in the cluster channels and are determined solely by the two-body scattering T matrices. These are constructed in accordance with the Pauli principle and correctly to account for the coupling between two-body channels as well as the energy shift in free resolvents G0. Such calculations have been previously performed for neutron and deuteron-induced reactions on lithium nuclei C12 and also oxygen 16. This for continues the investigation of the cluster structure of light nuclei in fusion reaction by solving a multi-cluster system of Faddeev integral equations in three-dimensional vector form. Particular attention is given for the treatment of Colombo repulsion in the energy region when the energy is less than 1 mega electron volt, and to evaluating the influence of the anti-scattering effect by a single atomic target nucleus is represented as a bond N minus D or P minus D system respectively, as well as more complex reactions, for example helium 3 and T and NP for the 5 to the power of 4 helium and helium 3 multiplied by helium 3 and 2p to the power of 4 and so on, in which both the target and the projectile are treated using cluster representations. Total across sections calculated between cluster modeling framework based on coupled multi-cluster Faddeev equation providing a unified descriptions of elastic scattering rearrangement and three-body breakup are compared with experimental data. The paper is structured as follows. The second chapter introduces the fundamental elements of three-body dynamics in momentum space and outlines the models and techniques for obtaining T matrices in the two-body sectors. The third chapter provides a measurement of the Colombo interaction, contribution to the total cross-section, and the role of screening parameter. Finally, the resulting cross-section for two and three body channels in the energy continuum, accounting for the coupling between various cluster channels and Colombo effects are presented in the both chapter. So thank you so much for watching my tutorial video until the end. This chapter was something about nuclear fusion, which was between the various cluster channels and Colombo effects. Today is 17th of June 2026. Time is 11:04.